Let us start the next practice on PCA, that is the analysis of some Forex data. Forex is foreign currency exchange market. So let's see how it looks like. So we first load the data. We see that we have almost 500,000 entries. So let's see what they are. So they are in periods of 15 minutes. So every 15 minutes we record what is the return. So the return is the gain or loss of a currency with respect to another. For instance, here it is the euro versus the Swiss franc. So in these 50 minutes, the open to close in one period. This is what this notation means. So it opened at a price, the euro to Swiss franc opened at a price and the close was at a different price. And the ratio between those two prices were 1.0002. So these are called pips. So pips are the fourth decimal digit. So you have gained two pips here. Here you would have gained 6 pips, 4 pips. Here you would have lost 8 pips, and so on. So we have different currencies here. So we have euros, we have Swiss francs, we have Japanese yens, and we have US dollars. We don't have all versus all combinations, but we have recorded data every 15 minutes of a few of the combinations. Okay, so and we have 500,000 of those. And then let us see what we do next. So what we do is we explore the data and we are trying to plot it. So we see that they are not completely independent. So completely independent means that you would see kind of cloud, Gaussian cloud here, but you see that these clouds have shapes. So these shapes mean that that there are some relationships that you can try to capture. That is what PCA will try to understand. How many real driving forces are underneath this data, and then you see these forces manifested in different variables as the ones we have been talking. And for instance, some of them, they are very clear. So for instance, the euro-dollar relationship is very much related to the dollar Swiss franc. So when the euro dollar is high, the larger the US dollar Swiss franc, the smaller will be the euro dollar. Okay, so this is how the data looks like. Then we do the PCA. For doing the PCA, we will constrain ourselves to just a few variables, only 30,000, because otherwise it takes too long. And then we will take the data, the numeric data, just corresponding to those 30,000 entries. So, and then we will do some plots, we will do some box plots, we will analyze the covariance and the correlation matrix, we'll do the PCA and analyze the PCA, the first two components of the PCA. Okay, so let's run the section. Okay, so here we have the covariance matrix. So because those variables were in pips, so the covariances are very small. So the standard deviation is in the order of 10 to the minus 6 or even less, 10 to the minus 7. So remember that the pip was 10 to the minus 8, 10 to the minus 4. So the variance is 10 to the minus 8. in the order 10 to the minus 8, and actually that is what we see. So this is 9, 10 times 10 to the minus 8. And then we have the correlation. We see that some of the variables are very much correlated. This is the one that we mentioned before, and positive or negative correlation doesn't matter. As what is important is the absolute value of the correlation. It doesn't matter in the sense that it is a strong correlation, and then we also have some other strong correlation here. Then we had the box plots. We have the box plots here. So we have all of the values were very much centered around 1, and then we have the different variables at the different box plots. And we see that most of the times the values are within just 10 pips. And then what else do we have? So we have a plot of the different periods over time. So let us make a zoom so we can take a region, and we see, for instance, we don't know which one is which. I cannot move this bar, but for instance, this might be probably the two currencies that or the two pair of currencies that we saw before. So for instance, when the euro dollar is or the dollar yen is going up, then the euro dollar is going down, and we see these peaks here. Probably they are very much related to that. We also saw in the covariance matrix and the correlation matrix that there was other two variables that were very much correlated, and these were very much anti-correlated, and we see that in this peak. So we see that these two are very much correlated, while this one is anti-correlated. And so this is how it looks like over time. And then what else do we have here? So we have here the script plot. So the script plot, we see that with two components we are explaining 86% of the data, and with three components we are explaining almost 100% of the data. And the fact that we have four currencies make that we don't have four the independent degrees of freedom. Actually, we have three. It is a kind of circular relationships. So we can try to analyze these two principal components and see how they look like. So those are the loadings of the different ratios in these principal components. So we see one in which the euro yen is opposed to the euro dollar. So all pairs except the euro dollar have positive sign. The other one is negative, and this one is the one that we have been commenting. So this is the opposite relationship between the euro dollar and the dollar Swiss franc. And there is an interesting property of PCA, that is that we can use it to reduce the noise. So we have been saying last components probably they are mostly noise. So just the first three components typically, or up to the point where you explain 80–90% of the variability, those are useful components, the rest is noise. So the point is that we can use PCA to denoise the input variables, and to do that what we have to do is to use the projections. So you know that we take the original observations, we take the principal components, we project onto the principal component space, so we have these projections. But now I can use these projections, but just for the two first components, multiply by the component itself, and then I'm back in the space of the input variables, but now with fewer variability because I have not used all the components that I had. So that is what we'll do. So for doing that, we will start by looking at the projections. So those are the projections of the input 50 of every input observation that we know that they correspond to 50 minutes. So we project them onto the first two principal components, and this is what we see. So we see a beautiful Gaussian, and now we can compare these to the plots that we had at the beginning where we saw clear shapes. Now these two principal components are independent of each other, and then we can reconstruct, and for doing that you don't have to fully follow the mathematics here, but what we are doing is first we are making this projection, making this multiplication of the score times the principal components, and then we have called this x hat. It is an approximation to x. X was our original variable, and we have kept we have kept the mean, because this is centered around 1, and then we have kept the mean. You may remember that PCA is subtracting the mean, so if you want to reconstruct, you have to add the mean. So that is what we are doing. We are adding back the mean so that now x hat has exactly the same, not exactly, but similar values to the input x before. Okay, so then we will make some plots over time, and then let's see how they look like. Okay, so let's run the section. So this is, for instance, the reconstructed one of the original variables. So we are plotting the original Euro Swiss franc relationship with respect to the reconstructed Euro Swiss franc relationship. Remember that a perfect reconstruction would mean having a line that would be the identity line. So we are away from the identity line, not too far away, but we are losing something. So it is obvious that we are not reconstructing exactly the same. And then also here we have a plot or two graphical ways of representing the reconstructed variables. So we have here the original variables and here the reconstructed variables, and we see that the kind of pattern look more or less the same. Probably the colors do not, but the reason of that is that here there are many more outliers, while here we have removed the noise, and probably all the high peaks and low valleys we cannot reproduce well, and then it seems that there is more contrast between nearby values, but otherwise they look the same. This is a graphical way of representing that. Here is another graphical way, so we can take this one and analyze a particular period. So we see that we have reconstructed pretty well. These are the original variables, these are the reconstructed values, and we see that they really follow the original ones. But now we have only two sources of information, the two sources given by the principal components. And the last plot we wanted to do was a B-plot now in 3D, and there is a problem here, that is that it has too many variables. So this 30,000 is a problem. but well, we'll see. It is a problem to rotate the plot. Takes too much time. It is too slow. So here we are. So I cannot rotate it because it takes too long. But what we see is that we almost have these euro, dollar, and dollar yen in opposite directions. This is something we saw at the beginning. And then we have in an orthogonal direction, we have the dollar Swiss franc that has a different source of information. Different sources of information are related to different driving forces. So there is a driving force that is, let's say, governing this euro dollar yen, and then there is another one that is related to the Swiss franc. It has a different dynamics than the rest of variables, and this is what we can get from this figure. And yeah, and then you may use the denoised relationships to take your decisions of investments for the future, or you can do whatever. But PCA, so we saw PCA in the previous example as a way to understand the underlying sources. Here we have used make use of it for the same purpose, but also we have added a new feature of PCA, that is, it can reconstruct without or with fewer noise or with less noise the input variables, so that we can analyze better and concentrate on important relationships between variables and observations. So that would be all, and see you in class.